In this video, I'm going to talk about two topics. I'm going to talk about the Sieve of Eratosthenes, and then I'm also going to talk about the concept of inclusion exclusion. This is really the same topic in my opinion. It just gets a really interesting Greek name associated with it. And something that is very interesting about number theory is the Greeks. Yes, the Greeks did a lot in number theory. You will find it with the Euclidean algorithm. You will find it in multiple places in number theory. So what's a sieve? Well, a sieve selects from something and leaves you with less, right? And so if you're looking for primes, I think an easy way that I like to do these sieves is just do the first 20 natural numbers. And I'm going to draw this very bold N, right? So this is really, let's just call these I. These numbers are all members of, right? This symbol means member of the integers. And I'm just going to go only up to 20. All right. And we're going to pick primes. Let's find primes. All right, so 2 is the one and only even prime. That's it. That's it. There are no other even primes. Every other prime is odd. All right, we know 3 is a prime. Of course, 1 is not a prime because it is not the factor of itself and another number. So the 2 has as a factor 2. 1 doesn't really have any factors. So it's really 2, 3, 5. I hope I said that right. 7. All right, so those are primes. 4 is 2 times 2, so it is not a prime. 6 is 2 times 3. 8 is 2 cubed. 9 is 3 squared. 10 is 2 times 5. All right. Now, already with the first row, we can wipe out whole rows of numbers that we're never going to look at. Anything even, we're never going to look at. Okay. So anything that ends in a 2, a 4, a 6, an 8, or a 0, these are all even numbers. None of them ever are going to give us primes. Okay, so we already knocked out half the numbers that we would ever look at right there in one fell swoop. Now, 11 is a prime, 13 is a prime, 15 is not. 15 is 3 times 5. So there you go. Every multiple of 5. 5 is a prime, but every multiple is not. So actually, we've knocked out 60% of the numbers. And sure enough, 17 is a prime, and 19 is a prime. So those are our primes so far. Now, what we can do moving forward is just start rows where we only do, okay, let's just do a few more. The 1s, the 3s, the 7s, and the 9s. Okay. And I recommend strongly to you to do this for yourself for fun. I know if you want to have some relaxation time with numbers, which us math geeks like to do, this is a good exercise. So the thing to do is to start doing multiples of all the primes that are odd. So 3, right? So we already went all the way to 9, right? So we know that, I'm sorry, this thing went a little crazy on me. Let's do the eraser. Sorry about that. Let's get back to normal with a 9 here. So we already did 9. We already did, it's only the odd powers, because of course, any number multiplied by any number, either odd or even, multiplied by an even number, is going to be an even number. So you're really looking for 3 times 5, 11, 13, 15, 17, 19, 21, and so on. We'll do all these and you'll see. So 15, we already know it's not prime, of course. Then 21, so we go over here and say, 21 is not prime. We already knew that, 3 times 7 Then 3 times 11, not prime. Let's knock it out. Not prime. Then 3 times 13 is 39. There we go. Not prime. 3 times 15 is 45, but it's already a 5, ends with 5, so we already discounted all of these anyways. 3 times 17 is 51, right? 21 plus 30. So that is 51. There we go. Now let me start up the other ones as well, going up to 100. So those are my rows to 51. Let me write out 61, 71, 81, and 91. Because I'm going to keep going. Oh, that was not right, was it? Why would I ever do that? And why would I ever do that too? Yeah, let's go this way so I don't get tripped up. 73, 77, 79, 83, 87, 89, 93, 97, 99. And we know 100 is not prime, so really up to 100, we already know 100 is not going to be one of them. So let's keep going. So let's do the threes again. We stopped at 51. 3 times 9 is 57, right? 30 plus 27 is 57. So we go over here. No, we're done. Then 3 times 21 is 63. All right, so that's in our next group, and it's right here. Now, that was 3 times 21, right? So let's do 3 times 23. This is 69, right? 69 it is. 69 is not prime. 3 times 25 is 75. We already discounted all the 5s. So really 3 times 27, which is really 60 plus 21 equals 81. Is that right? Yes, it is. 81 is not prime. Of course, we already know it was 9 squared. So that's an easy one. Then 3 times 21. This is a tricky one because this is 60 plus 27 equals 87. So sure enough, 87 is not prime. Then 3 times 31 takes us to 93, not prime. And then 3 times 33 takes us to 99. That's an easy one. So we're done with all the 3s. We were not going to do 5s. We already said that. So let's start running through the 7s. Now we stopped at 21, which is 7 times 3. 7 times 5 is 35, which is we don't need to bother about that. 7 times 7 is 49. 7 times 9. Right, so we can do more like this, is 63. 7 times 11 is 77. What is 7 times 13? That happens to be 70 plus 21, which is equal to 91. Okay, and then what's 7 times 14? I think we're over 100. 7 times 15 is 105, so we're over 100. So we're done with 7s. Okay, so now let's do 11s. 11s are easy in the sense that we don't have to really multiply them out. So it's 33, 55 is already taken care of, 77, and then 99. So we already took care of those. Do we have every prime by now? I think so. Let's check 13s just to be sure. So what about 13s? 13 times 3 is 39. 13 times 5 is a 5. 13 times 7, we took care of it with 7. 13 times 9, what's 13 times 9? Goes over already, right? So it's 90 plus 27. So I believe we are done. And I think these are the primes. Wait, this is 9 times 3. I'm sorry. I forgot that one. So then we had 2, 3, let's count them. 2, 3, 5, 7, that's 4, 5, 6, 7, 8. So there's 8 primes so far. I'm gonna put how many I have because I know I need to have a certain number. And this will tell me if I got as far correctly. So 23, 29, 31, 37, 41, 43, 50, 47, 53, and 59. So that's 2, 4, 7, 9. That's 9 of them up to 59. It's 9. And then when I go up to the remaining numbers as 2, 5, 7, 8. 8. And that happens to be the correct number, which is 25. There's this function called pi, and pi of 100. The total number of primes up to a number is 25. So we're done with the sieve of Eratosthenes. And now we can move on to inclusion, exclusion, and I'll do the simplest possible example of it. Okay, so what is inclusion, exclusion? It has to do with what numbers divide up to a certain number. Let's just do, I think 100 is a good example. So the way to calculate this is with what's called the floor function. What is the floor of 3.5? The floor of 3.5 is 3. You take out the part that's not an integer. All right. Now the floor function is tricky with negative numbers. Okay. The floor of negative 3.5 is not negative 3. It's negative 4. All right. But we're not doing negative numbers here, but I just wanted to mention it. Also, there's the ceiling of 3.5, which is 4. But in number theory, usually we're really only concerned with the floor. And the floor function is really done like this. So we don't do it with, because we don't really care about the ceiling. We're really doing the floor. So how many numbers divide, let's just do 10. Let's do 10, so it's simple. How many numbers divide 3? Divide 10 by 3. So we know, are divisible by 3 up to 10. Yes. So that would be 3, 6, and 9. So of course, the floor of 3.3 repeating, sure enough, is 3. All right. Well, how many numbers up to 10 are multiples of 5, are divisible by 5? That would be 5 and 10. Sure enough, this is 2. How many numbers divide up to 10 are, I'm sorry, and I keep doing this sometimes, so I'll stop here and not do that. How many numbers up to 10, yeah, actually I did it correctly, yeah, so there's only 1. There's just 7. 1 because it is 7. Okay, so now we can set up a little Venn diagram that goes like this. These are supposed to be circles, but they sure are not. They're close. All right, so these are the numbers up to 10, right? Up to 10. And I'm doing a few primes. For 3, okay, we had 3, 6, and 9. For 5, we had 5 and 10. And for 7, we had 7. All right, so here's something that happens with these small numbers. You have in this set, these are sets, you have 3, 6, and 9, you have 5 and 10, and you have 7, and guess what? There are no intersections. There aren't any numbers under 10, right, that are divisible by both 3 and 7. This is 0. There aren't any numbers under 10 that are divisible by 5 and 3. This is 0. And there aren't any numbers up to 10 that are divisible by 7 and 5. So this is a very trivial example of inclusion exclusion where there's nothing here really. These are 0, 0, 0, 0. Now, when we take this inclusion exclusion concept to say 100, and we do it again for 3, for 5, and for 7, it starts getting a little interesting because we're going high enough where why did I even put 20? I meant to put 7 there. Oh, it's because I was thinking about 100 divided by 5, which is 20, right? So there's 20 numbers, there's 33 numbers, and there's what? Is it 14? What is 7 times 14 is 28, plus 70 is 98. Sure enough, it's 14, right? So then, when we try to do this Venn diagram for 100, it gets a little more interesting. Let me see if I can do better circles. Not sure that I can. Boy, are these not circles. Woof, not circles. Okay, so the number is 100. And we're doing 3. We're doing 5. And we're doing 7. Okay, so we know the total number is 33, but this part right here, this set, is not 33 because we're going to subtract from this number, the 33, the total number of the total numbers up to 100 that can be divided by 15 or by 21. All right, and we know that that's not 0. So let's go in here and start doing that. So we have 3, 5, and 7, right? So 15, 35, and 21. Those are the 3 numbers we have to subtract, the 3 sets. Now, there's yet another set, which is the one where it's 100 divided by 3 times 5 times 7, which is 105. And we know that that is 0. So here, we can already go in here and say there's nothing here. All right, so then what happens to 100 over 15? Isn't that 30 times, yeah, so it's really 6, right? Because this gives us 90, so it's 6. All right, so then we know that the number, let me make sure that I get this right, 100 over 15 is 6, so that number is right here, 6. What happens to 21? It's 4, right, because it's 84. What happens to 35 is 2 because it's 70, 35 and 70. So then now we go in here, we take 33, and we subtract everything down here, and that's 10. So the number here is 23. And then here we have 20, right? But then we have 8, so this is really 12. And altogether we get 20. Then here, 7, we have 14. 14 minus 6 is 8. So our inclusion-exclusion diagram for the numbers up to 100 that are multiples of 3, 5, and 7 is in this Venn diagram. This is, and if you wanted to label them, this would be 3, this would be 3 and 5, this would be 3 and 7, and this would be 5 and 7, and this would be 3, 5, and 7. Now, I'm not going to do it in this video, but you can have a lot more fun when you do 4 numbers. Okay, because every one of these has something. And of course, you're going to need to do multiples where these primes, this product, and I like to do it with primes, so you don't have to do it with primes. This prime product will be greater than this number. And so there, if you did like say 3, 5, 7, and 11, this is 77 times 15, right? Which is really 77 times 10, and then 350, and then 35, which is really 1155, right? So I would pick something like, say, if I wanted to have fun with this, 1200, and do 3, 5, 7, 11. You should do this for yourself. Now, I'm going to give you a hint, or maybe I'll just tell you so that you think about it. When you do this, this diagram is missing 2 connections. All right? 2 connections. So this is not a complete diagram. When you do it for 3, what you see is what you get. Those are all the sets. But when you do it for 4, I'll say it. I'll just say it. You're missing this connection and this connection, because the 2-dimensional plot that you've drawn with your Venn diagram is not including the cases where something could be in this set and in this set. Because if you go through here, all the cases in here, and let's figure it out. Let's realize why what I'm saying is the case. Okay, so if this was 3, this was 5, this was 7, and this was 11. Okay, This is 3 and 5, right? This one here is 3, 5, and 7. This is 3, 5, 7. This is 3, 5, 7, 11. This is 5, 3, 11. This is 7, 11. This is 3 and 7. And this right here is 3, 7, 11. Guess what's missing? We don't have anything that says 7 and 5. And we don't have anything that says 3 and 11. So you gotta take care of those two. All right. So that is inclusion exclusion.